Hello my YouTube friends, today I would like to discuss why delta transformation and delta to Wye transformation and why this is important.
Every single day I'm gonna make something great. That's my way.
The importance of the Wye-to-Delta and Delta-to-Wye transformation is that sometimes the resistors may be arranged in such a way that they're in a delta format or they're in a Wye format. So what we call delta format is basically this is a delta symbol, and then the Wye symbol is this Wye symbol. Now, if resistances are arranged in this way, where they are connected to 3 nodes, and then it implies that there's a special way or special formulas that we use to convert or to handle these resistances that are connected in such a format. And this is what I'm about to show you just now. Now, this is the delta, like I mentioned. You've got the delta where you've got the resistors as RA, RB, and RC connected in a delta format. And then this is the Y. So you notice that this is like almost like an inverted Y. And this arrangement also can be converted into a delta. So if you're converting this into a delta, then you're going to connect your resistor from there connected to there, so it will form a delta like so. And if you're converting, so this can be labeled as RA, RC, RB. If you're converting this circuit to a Y, then between RB and RA, you're going to have a resistor which will come to the neutral point, and from that neutral point you have another resistor going all the way there, and another resistor will come here going all the way there. So this is your R1, for instance, and this is your R2, this is your R3. It depends on how you're sorting out the resistances. My numbering has got nothing to do. I'm just trying to ensure that my numbering matches the numbering on the other side. So this is the way the conversions occur. So by converting from a delta to Y, you can simplify the circuit and find the equivalent resistance much easier. In some cases, you're going to convert the Y into a delta, and you get a much easier approach to finding the solution to the equivalent resistance that you're looking at. Now, there are standard formulas that we look at when converting the delta to Y and the Y to delta. So beginning with the conversion from the delta to Y, so in this case we're converting the delta into the Y. And the standard formulas that are there is that to get, for instance, your R3, which is going to be located in between RA and RB, then your R3, which is this one here, R3, is simply equal to the resistances that are on the side of this new resistor that you're obtaining. We get that as a multiplication as the numerator. So this is RA multiplied by RB over the denominator, which is the sum of all the resistances in the delta circuit. So you've got RA plus RB plus RC. And this can be seen for resistor 3 from here. So you've got the numerator being formed by the resistances that are on both sides of the new resistor R3, which is RA and RB, becomes the numerator. The product of that is the numerator, and then the sum of all the resistances in the delta. And this is the same scenario that you notice when you come to R1, which is in between RA and RC. So you have RA and RC as the numerator, and then the denominator stays the same. So in this process, denominator stays the same. Okay, so this implies that this is not changing. RA plus RB plus RC is not changing for all the three cases that we have shown. If we come to look at the conversion from the Y to the delta, it's a little bit different. In this case, what we have, which is not changing, is the numerator. So the numerator stays the same. You notice for every solution, the numerator stays the same. So let's start by looking at, for instance, how we are obtaining RA. Okay, so for us to obtain RA, we're looking at forming RA in between these two resistances, R1 and R3. This is going to be RA. Now you notice that opposite RA is resistor 2. This resistor 2 is going to be the denominator for RA. So right opposite this resistor RA is resistor 2, which is the denominator in this case. And on the numerator side, we get the sum of the products of the two the resistances on each triangle side. So in this case, we've got R1, R2, which is this one, R1, R2. Then we've got R1, R3, which is this case. And then we've got R2, R3. So these three summations form up the numerator in this case. So this is our numerator that we obtain. And notice that the numerator is the same for all the resistances. Now, if we are looking for the resistance for RB, which is between R3 and R2, so the resistor opposite that is R1. So this is RB. The resistor opposite RB is R1. That is our denominator. Okay, and then the product, the sum of the products of R1, R2, R1, R3, R2, R3 stays the same as the numerator. Equally, when we come to the formation of RC, you notice opposite is R3, which is the denominator in that case. These are the ways that we use to convert a Y and delta or Y-to-Delta circuit. Now, these questions come in various formats. In most cases, you'll find these setups or arrangements of resistances in Thevenin's theorem, Norton's theorem, and basic equivalent resistances, where you have to find the equivalent resistance. But in most cases, you'll find these cases in Thevenin's and Norton's theorem, where after zeroing the sources, where you short circuit the voltage sources and open circuit the current sources, you notice that you are going to have, in some cases, arrangements of a Y and arrangements of a Y and arrangements of a delta. And how do we deal with such scenarios? So here is an example. For instance, we have this scenario here where you've been asked to find the total resistance between the terminals M and N. And if you notice here, you've got a back-to-back delta. So you've got a delta that is connected to another delta back-to-back, sharing one resistor. Now, to handle such a scenario, you can either convert the lower delta into a Y or the upper delta into a Y. Okay? And I'll show you how to do that just now. So if you look at this circuit, we've been asked to find between M and N. what I want to do is convert the upper circuit into a Y. And what I'm going to do is, you notice that for me to formulate a Y upper here, node C stays the same. I'm going to have a resistor there attaching to B, and a resistor there that attaches to node A. So in short, what I have is, what I'm going to have eventually is this circuit where I have a resistor that makes now a Y, and then this connects. So our node C maintains as node C there, and then we now have node B and node A maintained like so. And then what continues now here is we've got the RD and the RC meeting at node D and coming to N. So you've got N, M, this is node D. Now notice that what we obtain here, I can label as R1, I can label this as R2, and I can label this as R3. This maintains as RE, and this maintains as RD. What happens now is that you notice that R3 and RE are in series, R2 and RD are in series. Now, how do we get the value of R1? Okay, so R1 in this case is equal to RA multiplied by RB over the sum of RA plus RB plus RC, which in this case is equal to 30 times 50 over 30 plus 50 plus 60. And this is gonna give me 15. The base is 140, and this gives me 10.71 ohms. So R1 is 10.71, R2, which is this one between RA and RC, so you've got RA multiplied by RC over the sum RA plus RB plus RC. If I insert in the values, I've got 30 times 60 over, the base is the same, so I'm gonna just write 140 there, and when I multiply that, I get 1800 divided by 140, which gives me 12.86 ohms. And then I go get our R3, which is this one, is going to be equal to RB multiplied by RC over RA plus RB plus RC. This is equal to, the base is 140, then I've got 50 multiplied by 60. And this gives me 3000 divided by 140, which gives me 21.43 ohms. So these are the values of the resistances that we get. Then if we go further, you notice that R3 and RE are in series, and R2 and RD are in series. So series resistances simply add. So what we get in the next is that we've got the node C, we've got the R1, and then we've got two resistances that are now in parallel to each other, like so. So this is our R1, and now this is our R. We can label it anything, Rx for instance, and this Rx is the sum of, if you remember, we have R3 and RE as the RE plus R3. So this gives us, if you add, you've got R3, which is 21.43, and RE is 20. This implies that we have, so we've got 41.43 ohms. And on this side, if we take this as RY, it is equal to R. If you come back here, you notice R2 plus RD. So it is R2 plus RD. R2, we obtained 12.86, and RD is maintained at 40. So what we have on this side is 52.86 ohms. Now these two resistances are parallel, so what we get now, the final circuit is we get two resistances in series. So one is maintained as R1, the other one is can label it as RZ, which is equal to RY parallel to RX. So it is RX multiplied by RY over the sum of the two, RX plus RY, and this is gonna give us so you've got 41.43 multiplied by 52.886 divided by the sum of the two, and this leads you to a solution which is about 23.23 ohms. Okay, 23.23 ohms. And then we remember that R1 is equal to 10.71. So the final circuit now between M and N, which leads us to one resistor only, is this is the R total, or the final resistance, which is R1 plus RZ, and this is equal to 33.94 ohms. So this is the way you find the solution. The whole secret, if you come back, so this is your MN. So the whole secret was in the conversion of the upper part of the circuit, the upper delta, into a Y. Now, somebody may ask the question, what happens if I convert the lower delta? Will the solution change? No, it won't change. And for my students out there, I would suggest that you go ahead and solve the same question by converting the lower delta into a Y, and you apply the same principle as I have done to come up with these circuits and get to the final solution. I hope this will help your understanding on the Wye Delta conversions and Delta-to-Wye conversions. And so our solution here has been determined as 33.94 ohms. Thank you for watching. Please subscribe to this channel for more videos. Thank you. Good day.